Hi students, so today we are going to be starting our unit on looking at polynomials and properties of exponents. So for your notes today, you have a foldable, but I think the easiest approach that's going to be to do this is to not glue this in first and to just leave this so we can open up and write in it. But we are going to add something to the very top right above our notes. Okay, and what we want to add up above our notes is the idea that we understand just what our key terms and our key vocab are here that we're going to be looking at. So right up above where you would glue this in into your notes, okay, we're going to make ourselves a little key here to show us what these terms or these vocab terms are. Okay, so we're going to write this in. So the first key term is going to be whenever we have this small number up in the upper top corner, okay, that is our exponent. Okay, and an exponent tells us how many times we should multiply a number by itself. Okay, the next term is going to be whatever is receiving the exponent. So whatever has the exponent attached to it, that's going to be called our base. And then the number sitting in front of whatever is getting the exponent is our coefficient. Okay, and it's really important that we know these terms and they know what they refer to. So having those right up above where we have our list here is going to be super helpful so that we can do each of these properties. Okay, the big piece today, though, is that properties don't follow sort of the normal rules of math that we'd sort of think about. So in our first fold up here, we're going to start talking about what we do when we're adding or subtracting with exponents. And the key is that you already actually have been adding or subtracting with exponents for a long time. You just didn't know it. Because the reality is whenever a number doesn't have a variable, or number, I guess, doesn't matter, doesn't have an exponent at all, there is really an exponent of 1 sitting there. So up until this point, you've comfortably been able to say that 4x plus 6x is 10x because we've been doing that forever, right? We just didn't mention the fact that if there was no exponent sitting there, it was really a 1. And so if it had an exponent of 1 and we added it to something with an exponent of 1, we had an answer that had an exponent of 1. Okay, and so what we're going to recognize is that when we are adding and subtracting with exponents, what you've been doing for forever is that you're adding or subtracting the coefficient. You're adding the number in front, and then you're keeping the exponent the same. So if it was a 1 and we're adding it to a 1, it becomes a 1. Okay, so if we look at 5w to the 4th minus 3w to the 4th, this time we have subtraction. So the numbers in front, the coefficients, we're doing the normal math. 5 minus 3 gives us 2. And then we are keeping the exponent the same. So it was a 4, it's going to a 4, it stays as a w to the 4th. 18c to the 3rd plus c to the 3rd. Right, we're adding our coefficients, we see addition. So when we don't see a number in front, right, we also know that that's a 1. So an 18 plus a 1 gives us a 19. C to the 3rd to a c to the 3rd stays as a c to the 3rd. Now the big piece is then what happens if they don't match? Well, if the coefficients, if the bases don't match, okay, so for example, on example 4, we have a y and we have an a. Those bases don't match, so those can't be added. But that's also a true statement if the exponents don't match. Okay, so everything needs to match for us to be able to do this process. So if we look at example 4, the only terms that we can put together are this one and this one because those are our matching base and exponent. Okay, so if we do 8 minus 11, that gives us a negative 3. It was a y squared, it stays a y squared. Even though this is a 9a squared and it has an a squared on it, we still can't add them because they are different variables. So the bases have to match for us to be able to add. Okay, if we have something like 6x squared plus 5x to the third, we can't add these either. Okay, because our exponents don't match. And those bases and those exponents need to match for us to be able to add them. Okay, so when we're adding or subtracting with exponents, we're going to keep the exponent the same. We're adding or subtracting the coefficient, we're keeping the exponent the same. Okay, the next property that we are going to look at is what do we do if we are multiplying with exponents? Okay, so what happens if we have something like x to the fourth times x to the third? Well, if we break this down, we know that an exponent tells us how many times we should multiply that base times itself. So x to the fourth power really tells us x times x times x times x, right? 4 times. And x to the third really tells us x times x times x, so 3 times. So if we have 1, 2, 3, 4, 5, 6, 7 of them being added together, multiplied together, that means we would want x to the 7th. Now, it's going to be really annoying to go through and every time write down x times x times x times x, right? We don't want to do that. So what does it look like is happening here, right? We're taking this 4 and we're adding it to the 3. So when we are multiplying with exponents, we are going to add the exponents. Now, the coefficients still get the same rules. Those numbers in front still function as they always have. It's the exponents that then get added. Okay, and it's keeping these properties separate. That's the trick. Okay, that's the sort of key to this. So here we have 4b to the 5th times negative 3b. So the coefficients get multiplied just like normal. So 4 times negative 3 gives us a negative 12. That stays the same. The variables, we're taking those and we are adding the exponents. So the exponents do not have to match. We just need to add them. So this has an exponent of a 5, right? We said if there isn't an exponent at all, it is really a 1. So 5 plus 1 gives us a 6. So our answer would be negative 12b to the 6th. Now, we can have more than one variable in a problem. That's fine. Okay, so very common for us to see x's and y's, a's and b, whatever, multiple different variables happening. But the rule is still the same. So the coefficient in front, we are multiplying. 3 times 5 is 15. We can only multiply if they have a matching base. So that means I'm going to now look at where I see the same letter. So I see an x here, and I see an x here. So those can go together, so I'm going to add up the exponents. If I don't see an exponent, it's a 1. 1 plus 3 is 4, so that gives me an x to the 4th. And then I'm going to look at my y's, right? There's a y here, and there's a y here. 7 plus 4 is 11, so I'll get y to the 11th. So 15x to the 4th, y to the 11th. Big, small, short, long, the rule of multiplication doesn't change. This is the nice part about our properties of exponents, is no matter how long the problem is or how big the problem is, the rules are exactly the same. So the coefficients in front get multiplied. Now, if you're not sure with those coefficients in front, okay, so we're just going to multiply all of them. So we'll multiply a piece at a time, or you can type them all in your calculator or whatever, right? Negative 5 times 4 is negative 20. Negative 20 times negative 2 is positive 40. Just in some way, shape, or form, we're getting all of those multiplied. Okay, then we're going to go to our A's. Now, you might say, well, this one has A's and B's, and this one has A's, and this has B's. But keep in mind, this is really multiplication happening in between each of those. When we don't see a sign, it's really multiplication. So there's no problem with us reordering multiplication and saying, I have an a to the 3rd and an a squared, and a b to the 7th, right? It doesn't matter where they fall. As long as they have a matching base, they can be multiplied. So when we multiply, we add the exponents. 3 plus 2 is 5. 7 plus, we don't see anything, so that's a 1. 7 plus 1 is 8. So we'll get a 40, a to the 5th, b to the 8th. Okay, the last property we are going to look at today is what do we do when we have two exponents happening? We have a power to a power or an exponent to an exponent. So what do we do if we have something like y to the third all to the fifth? Well, we know that an exponent tells us how many times to multiply the base times itself. So y to the third all to the fifth power is really y to the third times y to the third, right? 5 times. And we already said that if we're multiplying with exponents, we want to add the exponents. So if we add these up, 3, 6, 9, 12, 15, this really gives us y to the 15th. But are we actually going to want to go through and do writing that out and then adding them all up, especially as the exponents might get bigger? That could be a really big pain. So what does it really look like is happening? Well, to get that 15, right, we're just multiplying that 3 times the 5. And so that's exactly what our property is going to tell us to do. Now, the key here that my students really struggle with is they're okay with multiplying the exponents. It's making sure that we understand we need to still give the exponent to the coefficient. So if we have something like 2g squared all to the 6th, this outside exponent gets shared with everything inside. So we really have 2 to the 6th power and g squared to the 6th power. So as we deal with exponents, exponents get big really fast. So you might need to use your calculator to do this. And if you want to type in any exponent, you're going to type in the base. And then right above the x squared, there's this 2 sides of a triangle. That's your up caret button. And then you can type in the exponent. Okay, so 2 to the 6th power gives us 64. And then an exponent to an exponent tells us to multiply. So 2 times 6 gives us 12. So we'll get 64g to the 12th. Okay, if we look at our next one, again, this outside exponent gets shared with everything on the inside. So we have a 5 squared, an a to the 3rd squared, and a b to the 5th squared. All right, we're sharing that outside exponent with everything. So 5 squared, you can use a calculator, but 5 times 5 gives us 25. And our rule tells us to multiply the exponents. So 3 times 2 gives us a to the 6th. 5 times 2, we get b to the 10th. Now we might look at example 4 and go, oh my gosh, that looks really big. But again, the nice thing about exponents is that the rules do not change. So even though the problems can get bigger or look longer, the property stays exactly the same. So we are still giving this exponent of 3 to every single thing in here. So we want 3 to the 3rd, c squared to the 3rd, over 2 to the 3rd, and y to the 4th all to the 3rd. Okay, so if we take 3 to the 3rd, we want 3 times 3, which is 9, and then 9 times 3, which is 27. You could also put that in your calculator. And we know with an exponent to an exponent, we are multiplying. So 2 times 3 gives us 6. If we look at the denominator, 2 to the 3rd power, so 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. And then we multiply our exponents, so 3 times 4 is 12. So we'd have 27c to the 6th over 8y to the 12th.